Hello everyone, welcome back. In this video, we are going to talk about the various types of pipelines. So continuing our previous discussion of pipelining, after taking a look at different types of pipelines, we will consider a few relevant exercises. So there are two major kinds of pipelines that can be found in computer systems. Those are arithmetic pipelines and instruction pipelines. Now, if you remember our previous discussion of pipelining, we have established so far that pipelines are used in operations where a larger task can be divided into subtasks, and then there's a possibility of executing those subtasks simultaneously, especially if they have to be repeated over and over again. And those kinds of opportunities are available in two distinct scenarios. Either we have a large arithmetic operation that can be divided into subparts, or we have several instructions that need to be executed, and those can be executed simultaneously. So that is why both arithmetic operations and instruction executions offer avenues for pipelining, and which is why we're going to discuss these two kinds of pipelines. So let's first start with arithmetic pipelines. An arithmetic pipeline divides an arithmetic problem into various subproblems for execution in various pipeline segments, right? So you can divide a big problem into small problems and then have a pipeline with multiple segments, and each segment will then take care of one of the subproblems. So the pipeline on the whole will result in the solution of the entire problem. These kinds of pipelines are used for operations like floating point operations, multiplication, and various other computations that involve multiple computations. So now if you remember how multiplication is performed within a computer system or how floating point operations are performed, you'll recall that these kinds of operations require performance of several sub-operations. Like, it's not like addition where you simply add two binary numbers. You have to perform smaller sub problems in order to solve the larger problem. So that is where arithmetic pipelines come in very handy. Such pipelines are found in very high-speed computers. Now again, it's important to remember that pipelining is hard to set up. It's expensive. Establish a pipeline, we require resources and circuitry, and since that circuit is only going to perform one specific operation, we have to be very sure whether we find that money or resources are more important than saving time. So these kinds of pipelines are found only in very high speed computers where speed, efficiency is more important than money. Alright, let's take an example. Let's try to understand arithmetic pipelines using an illustration. So let's consider floating point addition and subtraction, right? This is a problem that requires several steps, as you've already seen how floating point arithmetic is performed. So let's see how that can be done using a pipeline. If we consider floating point addition, you will recall that floating point addition requires binary numbers in this form, normalized floating point binary numbers, right? And if you need to recall how floating point addition and subtraction is performed, you can take a pause here, go back, take a quick look at the previous concepts, and then come back, because we're not going to go into the details of how this operation is performed. We're only going to look at how it is performed using a pipeline. The steps required to perform floating point addition should be very clear to you at this point. Alright, now let's see how this operation can be performed using a 4-segment pipeline. And this is what this pipeline is going to look like. So we can see that we have 4 segments, 1, 2, 3, 4. Each of these segments is performing some kind of operation, and if you take a closer look at this flowchart, you'll see that all of these operations are essentially what you do when you are performing floating point addition. These are all the steps that you must have performed by hand so far, and this is how it's actually done within the computer system itself, but now we're doing it using a pipeline. So overall, we're going to take a look at each of these segments separately in a few moments, but overall you can see that here we have the exponents, right, the mantissa, we have registers at each intermediary state, and within the registers, some operations are being performed within each segment, right? 1, 2, 3, and 4. And then you get the final result here. So now what we're going to do is take some example of these x and y and see how this pipeline performs addition of those two numbers, and see how what steps each of these individual segments is actually performing. Now, before we begin, first note that for the sake of simplicity, we are considering decimal numbers instead of binary numbers, and that is just for the sake of simplicity, because if we use for this illustration proper binary numbers, the computations will become very complicated. And since the point of this example is to show you how arithmetic pipelines work rather than how floating point addition is performed, so what we're going to do is, instead of using such numbers, we are going to use decimal numbers, again just for the sake of simplicity. This is essentially what this pipeline will do, but instead of doing this for decimal numbers, it is in reality it's going to do it for floating point binary numbers. So let's see what the first segment does. Now in segment 1, the input is x and y, which you can see. The exponents, which is 3 and 2, are stored in this register. The mantissas, which is this and this, are stored in this register. And then in segment 1, the exponents are compared by subtraction. Now you have to, in each of these steps, you have to keep recalling how floating point arithmetic is performed. So you just recall those steps and then try to translate them to whatever is happening in these segments. In segment 1, first step is to compare the exponents, these a and b, which were put in this register. That is 3 and 2. And you can see that the result is 1, right? Again, continuing from what you've learned about a floating point addition, the larger exponent, which is 3, is chosen as the exponent of the result. So whatever result we get, this is going to be the exponent of that, right? Now, segment 2. Segment 2, first, the result of segment 1 is stored in this register, and then this difference is supplied to this part of the segment where the mantissas are aligned based on whatever difference you got after subtracting the exponents. So in segment 2, one of the exponents is chosen, the larger one, which is 3, which we did here, and then the mantissas are aligned, right? In segment 2, mantissa of y is shifted to the right because y had the smaller exponent. So its mantissa has to be shifted so that both of these can be made the same. Again, this is the same concept that we used when you have already discussed floating point addition. The exponents have to be same. So that's why the mantissa of this number has to be shifted so that they become same now. And that is what's being done in segment 2. Then in segment 3, the two mantissas are added. You can see here in segment 3, we have to add the mantissas since we're talking about addition. If we had been talking about subtraction, we would have to subtract the mantissas, right? So since we're talking about addition, we add the mantissas and we get this new number. The exponent will be the exponent of whatever the larger number was. Now this is the exponent, this is the added mantissas. The result again is stored in a register. Then in segment 4, the sum is adjusted. The final result you obtain, this one, is adjusted by normalizing the results so that it has a fraction with a non-zero first digit, right? So the first digit has to be non-zero. This is done by shifting the mantissa once to the right and incrementing the exponent by 1 to obtain this. Now, again, the same concepts that you've already done when we're talking about floating point addition. This is just to show you how that operation is done using a 4-segment pipeline. Now let's take an example to see what kind of benefit this pipeline offers. So we could have performed the same operation using a non-pipeline system where no segments were involved and there was just one circuit that performed the entire operation in one go. So why should we use a pipeline? Consider, for instance, that the time delays for the 4 segments in this pipeline are 60 nanoseconds, 70 nanoseconds, 100 nanoseconds, and 80 nanoseconds. For example, suppose these were the time delays of these 4 segments. This is the amount of time each of these segments is taking to perform its assigned sub-operation. And then each of these registers are taking additional time delay of 10 nanoseconds, right? If you had to choose a clock cycle for this segment, and you know this from the previous video, the exercises that we discussed in the previous video, in case of a pipeline system, the clock cycle is chosen to be first the register delay, and that is added to whatever the largest delay in this entire pipeline is. So whichever segment takes the largest amount of time, the longest to perform its sub operation, is added to the the register delay, and in this case that is 100. And the reason for this, again from the previous video, it must be clear by now that the reason we choose the largest delay is because we know for sure that the time it takes for segment 3 to complete its operation, all three segments will have already completed their respective operations because they all take less time as compared to segment 3. So the largest delay of all of the segments, among all of the segments, plus the register delay, is taken to be the clock cycle. So in case of a pipeline system such as this one, it comes out to be 110. Now consider that there was a equivalent non-pipeline system that also performed the same operation. The delay in that case, the clock cycle would have been 60 plus 100 plus 70 plus 80. Again, this is something we discussed in the previous video. That would have come out to be 320 nanoseconds. So 320 ns is the time for the non-pipeline system, and 110 nanoseconds is the time it takes to perform the same operation in a pipeline system. So if you compute the speed up, that comes out to be 2.9. So a pipeline system is 2.9 times faster than an equivalent non-pipeline system. If you had performed the same floating point addition using a non-pipeline system, it would have taken 2.9 times more than this system takes. And that is the clear advantage of using an arithmetic pipeline. Another advantage, aside from the speed up, is that using this you will be able to perform addition or subtraction of a stream of binary numbers, right, simultaneously. Now let's talk about instruction pipelines, the second kind of pipeline. Now again, see, instructions within a computer system at any given time you have to perform multiple instructions. So rather than waiting for each instruction to finish and then picking up the new instruction and then picking up the new instruction, rather than doing that, you can try to execute them simultaneously, and that is what an instruction pipeline does. An instruction pipeline reads instruction from memory while previous instructions are being executed in other segments of the pipeline, right? Thus, we can execute multiple instructions simultaneously, thereby increasing the throughput of the computer system. Throughput is number of instructions executed per second, right? So by executing multiple instructions at the same time, we can increase the throughput. Now, instruction pipelines are most efficient when the instruction cycle is divided into segments of equal duration. And we've already discussed this in the previous videos. Pipelines are most effective. The speed up that you get using a pipeline is the highest when you can somehow make sure that each of the segments takes equal time to perform its operation. Although in reality it's much harder to implement because there are even the tiniest delays between the execution times of various segments, but it's the most efficient. If you can achieve that, then that is the most efficient way to have a pipeline. If all the segments are of equal duration, that is the most efficient pipeline. Now here's an illustration to just give you an idea of how a pipeline system looks in contrast to a non-pipeline system. Then normally what happens is you have, and suppose we are going to execute 3 instructions. So in a non-pipeline system, instruction 1 is executed. You have to wait until the end of the execution of instruction 1 before you can start the execution of instruction 2. And then you have to wait till the end of the execution of instruction 2 before you can start the execution of instruction 3, and then that instruction ends. So this is the total time it takes to execute 3 instructions in a non-pipeline system. On the other hand, if you were using pipelining, you see instruction 1 is being executed, and then after some time instruction 2 starts, and while instruction 2 is being executed, instruction 3 starts. Instruction 1 is also currently being executed, you can see here. And in this case, This is the total time it takes to perform these 3 instructions. The number of instructions is the same, the length of the instructions is also the same, but you have considerably reduced your time, and time within a computer system is essentially clock cycles. So now you're able to perform the same operation but with reduced number of clock cycles. Next, we're going to take a look at how to design a very simple instruction pipeline, just like we did in case of the arithmetic pipeline, just a design example. But before we do that, we have to take a quick look at the sequence of steps involved in an instruction cycle. So first step is to fetch the instruction from the memory. The second step is to decode the instruction. This step tells us what this instruction is all about, what actually we have to perform now. The third step is to calculate effective address of the operand. The fourth step is to fetch these operands from memory now that we have the effective address. The fifth step is to execute the instruction. So now that we know what the instruction is actually telling us to do, plus we have the operands, we can execute the instruction. And the final step is to store the results of the computations of the execution in a proper place. Now let's see how we can design a 4-stage or 4-segment instruction pipeline. Design of this pipeline is going to be based on 2 main assumptions. Assumption 1 is that the instruction decoding phase can be combined with the effective address computation phase. And see, what we're saying is step 2 and step 3 are assumed to be combined in one stage, right? We're just basically reducing the number of sequences. So now we have combined 2 and 3 in one segment. And then the assumption 2 is that most of the instructions place the result in a processor register, so that instruction execution phase and the result storage phase can be combined into one segment. So now again we have combined 2 phases into one segment. Those 2 phases are instruction execution phase and result storage phase. These 2. So these are the 2 main assumptions, very simple assumptions. First, 2 and 3 are performed in one segment, and 5 and 6 are performed in one segment. So we have one segment, 2, 3, and 4, right? So this is how we are designing a 4-segment instruction pipeline that essentially they perform these 6 steps, but since we have combined multiple steps into a single segment, we have a 4-segment pipeline. All right, so this is what such a 4-stage instruction pipeline looks like. This is the flow chart. So we can see segment 1, segment 2, segment 3, and segment 4. Now let's see how it works. The first step is fetching of the instruction from the memory, right? That is what the first segment does. So instruction is fetched from the memory. In segment 2, the instruction is decoded. The effective addresses of the operands, if there are any, are decoded, right? They're calculated. And then in the next step, the question we ask is this instruction a branch instruction? This step is important because this will change the flow of execution of a normal instruction cycle. So if you've studied instruction cycles, you know that whenever a branch instruction is encountered, the normal flow of operation of instructions is hindered. So if you had 100 instructions and you were executing them sequentially, 1, 2, 3, 4, 5, 6. So this execution sequence will remain intact as long as there is no branch instruction, because once a branch instruction comes in, it will take you to another instruction. If you encounter, suppose, a branch instruction at step 5 and it says that you have to go to instruction 78, so all the instructions from 6 to 77 will not be executed, right? So that is how branch instructions break the chain of sequence. So the next question after decoding the instruction, because once you decode the instruction, only then you will know what kind of instruction it is. So is it a branch instruction? If it is not, then you move on to segment 3, which is simply just fetch the operands from memory. So we're going to take a look at this part later. For now, let's just say that after decoding the instruction, we find out that it is not a branch instruction, it's a normal instruction. So we move on to the next segment, and the operands are fetched from the memory because the address was computed here, right? In segment 4, the instruction is then executed, and then we check for interrupts. And the same thing happens that happened in case of the branch instruction. You know that along with the instruction cycle, interrupt cycles also go on in a computer system. So now after the execution of the instruction, you have to check for interrupts, because if we have an interrupt, then we have to handle the interrupt before fetching the next instruction, right? So if there is no interrupt, then fine, normal execution will go on, and we will go up again to segment 1 and we'll fetch the next instruction, and the same steps will then follow. We'll take a look at this later. Now see, while an instruction is being executed in segment 4, the next instruction in the sequence is busy fetching operands from memory in segment 3. That's how the pipeline works. So when one instruction is in segment 4, another one is in segment 3, another one is in segment 2, and another one is in segment 1, right? So when an instruction is in segment 4, the next instruction is in segment 3. Now, the effective address can be computed in a sequence circuit for the third instruction, and whenever the memory is available, the fourth and all subsequent instructions can be fetched and placed in the FIFO buffer, which means that up to 4 sub-operations in the instruction cycle can overlap with one another. And that means that up to 4 different instructions can be processed at the same time. So take a break here, take a look at how this specific pipeline is working, and you'll see that up to 4 different instructions can be present in various segments of this pipeline at the same time. That's the speed up you get if you use a pipeline system instead of a non-pipeline system. Okay, now let's talk about the branch and interrupt part that we didn't consider earlier. In segment 2, we are decoding the instruction. Now, after decoding the instruction, you'll find that we have a branch instruction at our hand, and this branch instruction, it causes a break out of the normal sequence. Now, if that happens, if the instruction you just decoded is a branch instruction, if it is not, the normal operation continues. But if it is, then the pending operations in the last 2 segments, because since this is a pipeline, it means that segment 4 and segment 3 are already operating on some other instructions when this new instruction was decoded in segment 2. That means both segment 3 and 4 are in the middle of something at the moment, right? So when a branch is encountered, the pending operations in segments 2 and 3, they are completed quickly, and the information stored in the buffer is deleted. If any information, this one that was stored in the FIFO buffer, it is deleted, because now the next instruction in the sequence is not going to be executed. Instead, we are going to execute whatever this branch statement says, right? So if you had previously stored any instructions in the buffer that you were going to execute next, will not be executed anymore, so they have to be cleared out from the buffer. Whatever was in segment 3 and segment 4 also has to be, they have to complete their operation, right? And then the pipeline will restart from the new address stored in your program counter. Again, the details being used to explain this pipeline are something which you have already learned. You know how an instruction cycle works. You know what happens when a branch is encountered or an interrupt is encountered, right? So the program counter is updated, the pipeline is emptied out, and then you go back and fetch the instruction, and this time you fetch the instruction that the branch statement is telling you to fetch, not the instruction that was in the chain earlier, right? And the same thing happens when an interrupt request occurs. This is the same thing. We have a system for interrupt handling. Again, this is something that you have learned earlier. The same steps then happen as they did in case of the branch instruction. The PC is updated, whatever was in the pipeline is emptied out, and you go back and then you handle the interrupt. And after the interrupt is handled, and then you start with a normal chain of instructions, whatever was in the docket already. And this is how a 4-stage instruction pipeline works. Alright, now let's try to understand the operation of an instruction pipeline using a timing diagram. So this is a timing diagram for a hypothetical instruction pipeline, and this pipeline consists of 4 segments. Let's say that this is a 4-segment pipeline, and the 4 segments are FI, DA, FO, EX. FI is the segment that fetches the instruction. FI, fetch instruction. DA is decode and compute EA. The decode and address, right? So this is a segment that decodes the instruction and it computes the effective address of the operands. Third segment is FO. It fetches the operands based on the effective address, and the final segment is EX. This is the segment that executes the instruction. So this is our 4-segment instruction pipeline. Now we're going to try and understand how a 4-segment pipeline normally operates. But before that, we have to take a look at this assumption. Now, as you must already be aware that only one memory operation can take place at the same time. For instance, you know that both instructions and operands are stored within the memory. The point is, when an instruction is being accessed from the memory, operands cannot be fetched from the memory because two different operations cannot occur on the same piece of memory at the same time, right? So when instruction is being fetched, FO has to wait, and when an operand is being fetched, FI has to wait because they both can't access the memory at the same time. But because the whole point of having an instruction pipeline is to speed up the things, right? So that one segment doesn't have to wait for the other segment, what we do is we have separate instruction and data memories. And that's a facility that can be set up within a computer system. So if the processor has separate instruction memory and data memory, then that means they are essentially two different parts of the same memory, which means they can be accessed at the same time. So instructions will be stored and fetched from the instruction part of the memory, and operands will be stored and fetched from the data part of the memory. And then FI and FO can occur at the same time. So if there is no facility to have separate instruction and data memories, then FI and FO cannot proceed at the same time. There will be a problem in your pipeline. But if you have separate instruction and data memories, then FI will only access the instruction part of the memory, and FO will only access the data part of the memory. So that means these two steps can take place at the same time. Now, for the sake of this pipeline, we are assuming that we do indeed have different instruction and data memories so that FI and FO can proceed at the same time. Now we're going to try and see what's happening in this timing diagram. Alright, now as long as there are no branch instructions, each segment operates on different segments, right? Let's take instruction 1. So in step 1, these steps are essentially, they count the clock pulses, right? So when the first clock pulse occurs, instruction is fetched. The first instruction in line, it is fetched. When the second clock pulse occurs, your instruction goes from segment 1, which was FI, to DA. So first the instruction was fetched, and now it is decoded and the effective address is computed, right? Now this instruction has moved on to segment 2. Another thing that happens when step 2 occurs is the next instruction in line is fetched, right? Instruction 2 is now fetched when the second clock pulse occurs. When the third clock pulse occurs, the first instruction, which was in DA phase, now moves in FO phase, which is operands are fetched. Instruction 2, which was in FI segment, now moves on to the next one, which is decoding and effective address computation phase, and so on. But this is only as long as there are no branch instructions. Normal execution takes place only when there are no branch instructions. Now suppose the third instruction in line was a branch instruction. What happens then? In step 3, instruction 3 will be fetched. In step 3, instruction 2 is being decoded. In step 3, instruction 1, operands of instruction 1 are being fetched, right? These 3 steps are being executed on 3 different instructions at the same time. Now, when the branch instruction is decoded, which happens in step 4, branch instruction, which was instruction 3, will be decoded, and it is at that time that we know that this is a branch instruction. So we don't know what this is in the FI stage, but in the DA stage, we now know that this is a branch instruction. But in step 4, you see, instruction 4 has already been fetched, because that's how an instruction pipeline works. When one instruction moves on to the next segment, the next instruction moves to the first segment. So when we found out that instruction 3 was in fact a branch instruction which was in step 4, fourth instruction had already been fetched, right? So the transfer from FI to DA of the other instructions, the next instructions after 3, have to be halted, because now we are not sure if we are going to execute instruction 4 or whether this branch instruction is going to take us to a new place, right? So unless this branch instruction is completely executed, which you can see happens in step 6, we have to halt the working of the rest of the pipeline. So instruction 4 was fetched, but it will nothing new will happen to this instruction, nothing further will happen to this instruction until instruction 3 is executed, right, which happens in step 6. So these dashes indicate halts. These indicates halts in your instruction pipeline. Halts are times when nothing is happening within a segment. So during step 5 and step 6, nothing is happening in this segment, nothing is happening in this segment, right? Now, if the branch is taken after the branch, instruction 3, is executed in step 6, if we decide that the branch is going to be taken, a new instruction is fetched in step 7. When this step occurs, the new clock pulse occurs, new instruction will be fetched. Whatever instruction the branch is taking us to, that will be fetched. But if the branch is not taken, then whatever instruction was fetched in step 4 can be used. So here we had already fetched this instruction, even though its operation had halted in the meantime until this was executed. If we're not going to take the branch, that means we have to continue with the normal sequence of instructions. So this is then executed, right? And then the pipeline continues until a new branch instruction is encountered. And again, if you encounter a new branch instruction, you have to repeat the same steps. You have to wait until the execution, and then you have to figure out whether or not you're taking the branch. And depending on that decision, then you either empty out the pipeline and bring in a new instruction, or you just start with whatever was fetched earlier. So this is how a instruction pipeline, very simply, how it works. Now, there are some difficulties involved in instruction pipelines. See, the advantages are clear. You increase the throughput of your system. There is considerable speed up, and that is good. But there are certain inherent difficulties involved with setting up and using an instruction pipeline. And the factors that prevent instruction pipelines from operating at its maximum capacity or being less than ideal are, number one, different segments may take different times to operate. So like we have established already, the most effective pipeline is where all the segments take the same exact amount of time to operate. But that doesn't happen in reality. So different segments may take different times to operate on whatever they're supposed to operate on, and that leads to some kind of performance leakage, right? Some segments may need to be skipped for certain operation. For instance, a register mode instruction does not need an effective address computation phase because the operands are in the register. They're not in the memory. Since they're not in the memory, there is no address to be decoded. So even though you have a pipeline and you have to make provisions for all different kinds of instructions, so you have to have a decode phase. But in case of register mode instructions, that specific phase is not going to be used. It's a wastage, right? So some segments may need to be skipped for certain operations. Again, this is keeping your pipeline from operating at its maximum capacity. And then 2 or more segments may require memory access at the same time. So we already know that if we have different instruction memories and data memories, then FI and FO can execute at the same time. But when 2 or more segments require memory access at the same time, one of them might have to wait until the other is finished if you don't have separate memories, or if you have 2 instructions which are being fetched from the memory at the same time. So even if you have separate memories, in that case, if you have multiple instructions being fetched from the memory at the same time, that won't work, right? So you have to wait. Alright, now let's take a look at some exercises to help get some better idea of how these pipelines actually work. Alright, so consider the 4 instructions in the following program. This is a sample program given to us. Suppose that the first instruction starts from step 1 in the pipeline used in figure 1. So again, you've seen this figure just now. Specify what operations are performed in the 4 segments during step 4. During step 4. This is step 4, right? What's happening in step 4? The first instruction is being executed. The second instruction, the operands are being fetched for that. For the third instruction, decoding is happening, and for the fourth instruction, it is still being fetched. So we have to show this for this. Let's see how we can do this. Right. So the first instruction that is given to us is load instruction. In a load instruction, simply, right, we can just put 1, 2, 3, 4 since we have to show what happens in the fourth step. So in the first step, this instruction would have been fetched. It would have been decoded in the second step. The operands would have been fetched in the third step. In the fourth step, currently, it is being executed. Then the next instruction comes along. This was the next instruction. So in step 2, this instruction will be fetched. In step 3, it will undergo the next phase, which is decoding. In the fourth step, the operands are going to be fetched. So no need to write the fifth step because we are concerned with what happens in the fourth step, right? So in the fourth step, it's currently in the FO stage. Then the next instruction starts executing, right? So in the third step, it will be fetched. In the fourth step, it's still in the decoding phase. And again, no need to write what happens after this. Finally, this instruction is encountered. And in the fourth step, it will still be executed. You can see this directly from here, right? This is step 4. This is what we are concerned with. So what we can see from this, what's happening in the fourth step? First instruction is being executed. That means memory word is transferred into R1, right? This memory word is loaded into R1. In for the second instruction, it is in operand fetch phase, which means what happens in this case if we are fetching the operands? This memory word is being read, right? For the third instruction, it is in the decoding phase. What's happening in the instruction 3? The increment instruction, right? So simply, increment instruction is being decoded. For the fourth instruction, it is still being fetched, right? So simply, this fourth instruction is still being fetched from the memory. And that is all you had to do in this question. Now we're going to take a look at some more examples, problems for this specific instruction pipelining, but for that we still need to go over some important concepts. So once we take a look at those, we will return to this original concept of instruction pipelining. For now, this is it. And just a quick recap. So we've talked about 2 kinds of pipelines in this video: arithmetic pipelines and instruction pipelines, and then we took a look at some relevant exercises. Again, more exercises will follow in the next video. In the next video, we are going to be looking into various kinds of pipeline hazards. So we'll talk about the types of hazards as well as the methods that have been established for the resolution of these hazards. And then we'll take a look at some relevant exercises.